Hi guys, welcome to Control Engineering, and in this video presentation we'll be looking at signal flow graphs. As usual, Maruf Motion is my name, and marufmotion@gmail.com is my email address. You can also get in touch with me on WhatsApp +263 717 535 I hope guys you are going to enjoy the way how a signal flows, that is signal flow graph. They are very important in control engineering. Let us enjoy. What basically is a signal flow graph, SFG? This is simply a pictorial representation of a system which displays graphically the transmission of signals in it, that is from one node to the other node, or from the input to the output, or from the output to the input when there is feedback. And what are we saying? A signal flow graph can be developed from a block diagram, but there is a difference between the two. In signal flow graphs, we'll be talking about nodes and branches. There are no blocks per se, and there are a lot of mathematical rules. So in signal flow graphs, all dependent and independent variables are represented by nodes, and all the lines joining the two nodes are known as branches. So you will be defining the elements that make up a signal flow graph very soon. Basic elements of a signal flow graph, and we'll start with input or source node. In this case, our x1 is our source node or the input node. And how can we define it? The node having only outgoing branches is known as the input or the source node. And in this case, x1 is the input or the source node. And this is there is no any other incoming node, hence x1 is an input or source node. We are saying a node represents a system variable and a branch connecting two nodes. For example, in this case, x1 and x2 are nodes, and a branch connecting the two, which is T12, it acts as a multiplier. And we are saying each branch is a gain, and this is the gain, or it is also known as the transmittance. And when a signal passes through the branch, it is multiplied by the gain, of course, as we know from our electronics. It gets multiplied by the gain of the branch network, and the signal flows in one direction only. What are we saying? We are saying from x1 to x2, signal flows in this direction. But there is a possibility that, for example, from x3 to x4, it is flowing in this direction, and it will come back in the other direction through minus t1. But you cannot have bidirectional communication between one branch. Please take note, this is an important point. A branch is associated with transmission gain. This is our branch, and A is our transmission gain. So it is associated with the transmission gain and an arrow. This arrow and the A, the gain. So we are saying the figure below shows a pictorial representation of a system having two variables, where the variable x2 is equals to this multiplied by the gain. So x2 is equals to A x1. Please take note of this. So we are saying A is the transmission gain, and this arrow shows the flow of a signal. And as we said, the branches of any signal flow diagram are always unidirectional. All the branches of a signal flow graph represent the cause and effect relationship existing between the variables. So what's the essence of this chapter on signal flow graph? We seek to introduce signal flow graphs in detail and its application to find the transfer function of complicated systems. We'll be able to do that. What is a sync node? Another name for a sync node is an output node. So we are saying a node having only incoming branches is known as a sync node or an output node. And let us identify a sync node or an output node. That is x9. x9 is our output node. Why? Because it has got only incoming branch. What is a mixed node? A mixed node is a node having both incoming and outgoing branches. T12 is this arrow is is incoming to x2 and its gain is t12 or its transmittance. This array is incoming to x3 with a transmittance of t23, etc., etc. So we are saying this has got incoming, outgoing, this has got this incoming and this outgoing up to x8. So these are our income, our mixed nodes. Mixed nodes are also known as chain nodes. Please take note. The other element that makes up the signal flow graph is the forward path. A forward path simply means the path from the input to the output, and you must be able to identify forward paths in a given signal flow graph, and we are now doing that. And let's identify the first forward path. This is straightforward. You go straight from x1 to x8. So it's x1, x2, x3, x4, x5, x6, x7, x8 up to x9. Then the second forward path is x1, x2. From x2 we go via t24 to x4, then x5, x6, x7 up to x9. Let's identify the third forward path. This is from x1 to x2, x3, x4, x5, x6. Then from x6 we go via t68 to x8, then up to x9. Then the last forward path, x1, x2, x4, x5, x6, x8. After x6 we go via this way up to x8, then x9. If you can closely check, we did not repeat any forward path. And if you are asked to identify how many forward paths are there in a given signal flow graph, you must be able to do that. Also have what we call the feedback loop or the feedback path, and we are saying if a loop or a branch originates and terminates at the same node, it is known as a feedback loop. For example, x3, x4, and then x3. This is a feedback loop. We are coming back, we are leaving x3 and coming back to x3. If we start from x2, x3, x4, x5, x6, x7, and when we get to x8, we come back to x2. We call this a feedback loop. So I can only see two feedback loops in this or on this signal flow graphs. Also have what we call a soft loop. What is a soft loop? This is a loop that consists of only one node. For example, in this case, x5 is a soft loop. We are leaving x5 and returning to x5 through the transmittance T55. What is a path gain? Guys, you must also be able to calculate the gain of each forward path or of each path. For example, the product of gains going through a forward path is known as path gain. The path gain for the first path, for example, in the previous slide, we identified the forward path, and this was our forward path, and we want to find out its path gain. So we are saying from there to there, its forward path is T12. We are now including the gains only. T12 times T23 times T34 times T45 times T56 times T67 times T78 times T89, and we are done. We can also be asked to find the gain of each path, of each forward path. Let's have a look at path number 2, gain of path number 2, and we are saying this is T12 times T2 T4. In other words, we are going from x1 to x2 and then to x4. So it's 2T4, then T34, T45, T56, T68, then from T68 to T89. The gain of the third path, which is path number 3, is T12 up to, let's go to T23, we go to T34, we go to T45, T56. When we get to T56, we'll go via this path, which is T68 and then T89. This must be our gain for the forward path number 4. That's T12, T4, 5. When we get to T5, when we go to X5, we go to T56, then T68, then from T68 to T89. So guys, there's no duplication. Let's close the check. There's no duplication there, and you must not duplicate. So this is how you this is how you find path gain. You simply multiply these gains along each forward path and you are done. Please take note that a self loop should not be considered while defining the forward paths we leave this T55. You cannot locate the gain of T55. What is a dummy node? We are saying if the incoming as well as the outgoing branches exist at the first and last node, we've got an outgoing and incoming branch, an incoming and outgoing branch. We call at the first and last node representing input and output variables. These nodes cannot be taken, so x1 cannot be taken as the input node, and x3 cannot be taken as the output node. If we want to identify them as input and output node, what do we do? A separate input and output nodes are created by adding the branch node with gains of 1. For example, we have created another node there with a branch node of 1 and another branch node of 1 there after creating these two additional nodes. These nodes are known as dummy nodes. Please take note that this node is a dummy node, this node is a dummy node because they were not there in this signal flow graph. When we look at Mason gain formula, guys, you must be able to identify non-touching loops, and we are doing that. We are saying if there is no common node between two or more loops, then these are known as non-touching loops, and we are saying we've got two non-touching loops and there's no common node between x3, x4 and x3 and x2, x5 and x2. These are loops. Let's go to B. These three loops, 1 loop, 2, 3. There is no common node between the three loops, so we say we have got three non-touching loops, but we don't have any non-touching loops on fig C because x3 is common to this loop and also to this loop. X4 is common to this loop as well as to this loop, so we are saying there are no non-touching loops. So guys, take note of these loops and you must be able to identify non-touching loops on a signal flow graph. Non-touching loop to a forward path. We are saying if a loop does not touch a forward path, in this case this is the forward path and this is our loop, this is our soft loop and this is our forward path, and we are saying if a loop does not touch a forward path, that is no node is common between a forward path and a feedback loop. This loop is a non-touching to that of the forward path, and we are saying this figure shows non-touching loops to the forward path, and we are saying this is our loop, this is our forward path, loop non-touching to a forward path, so this loop is non-touching to this forward path, this soft loop is non-touching to this forward path. Please take note. We looked at the gain of forward path. We are now having a look at the gain of loops, feedback loops, and we are saying it is defined as the product of all gains of the branches forming a loop. In this case, it's T22 times T32. T22 times T32 as shown for this loop there. For this loop is T23 times T32 as shown, and for this loop is T44, because we are coming back, we are going 3 from x4 and coming back to x4, so there's only one gain, T2, T44, and we call this a soft loop. Let's discuss rules for signal flow graphs just as we did rules for block diagrams, and we've got what we call the addition rule. And the addition rule, the algebraic sum of all signals entering a node gives the value of the variable of that node, and this is called the additional rule. And let's talk of x4. Additional rule according to x4, it says that ax1 plus bx2 plus cx3 plus dx4 plus ex6 gives us x4. We are saying the value of the variable represented by a node is equal to the sum of all the signals that are entering that node, as we have demonstrated in this algebraic sum. And in this case, please take note that there is no outgoing branch. We've got the transmission rule, and the transmission rule goes: the value of a variable at a node in signal flow graph is transmitted on every branch that is leaving that node. And we've got x2. What is x2? x2 is equal to ax1, x3. x3 is equal to b times x1, x4 is equal to c times x1, that is x5, x5 is equal to d times x1. So we are saying the value of a variable at a node in a signal flow graph is transmitted on every branch that is leaving that node. Incoming signal to a node through a branch is given incoming signal to a node. The incoming signal to a node So the incoming signal to x5, the incoming signal to x3 is given by the product of a signal variable at a previous node. This is the previous node, this is the previous node, and the gain of the branch. For example, this x3 is equals to a1 x1 plus a2 x2. This says it all. The incoming signal to a node through a branch is given by the product of a signal at a previous node. This, in this case, is x1, and the gain of that branch, which is a1. Please. Just as what we did for cascaded blocks, we are going to do the same for cascaded branches. They can be combined to give a single branch whose transmittance or gain is equal to the product of the individual branch transmittance. In other words, from x1 to x5, we have got this transmittance A, B, C, D. So we are saying we have combined the transmittance between x1 and x2, x2 and x3, x3 and x4, x4 and x5. And we now have got a single branch, which is this branch, and the transmittance is equal to the product of A, B, C, and D. Another rule, and this rule applies to parallel branches in the same direction and connecting two nodes. We are saying it can be replaced by a single branch with gain equal to the sum of the gains of the parallel branches, just as what we did for blocks connected in parallel. So we are saying y1 is a node, y2 is a node, and we've got these branches A, B, C connecting these two nodes. So we are saying these three branches are in the same direction, so they are going to be replaced by a single branch, which is this branch, and what has happened to gain A, B, and C? It has been replaced by gain that is equal to the sum of the gains of the parallel branches. This is easy, guys. We've looked at this rule, and we are saying a series connection of unidirectional branches. This is a series connection y1, y2, y3, y4 can be replaced by a single branch. This is a single branch with gain equal to the product of the branch gains. A1 times A2 times A3 is going to be the gain through this one branch. So it's a rule that can be used to replace a series connection of unidirectional branches by just a single branch. This is just a single branch. We've looked at a mixed node in a previous slide, and we said it is also known as a chain node. And in this case, we're going to eliminate a mixed node. How do you eliminate a mixed node? By multiplying the transmittance of the outgoing branch, which is C, with the transmittance of the incoming branches A and B. So in other words, A times C, A and B and C. If we've done this, we have eliminated the mixed node. So please take note of how you eliminate the mixed node. Then we also have a rule for loop elimination. We want to eliminate this loop. So how do you eliminate the loop? You write equation at the input and also equation at the output, and you rearrange to find the ratio of output to input. So in other words, this is how you this is identical to this, but for clarity, let's proceed to the next slide and see how you go about it. Let's see how you can eliminate the loop. I want to move this. So how do we find x2? We've got input and output. So it's ax1 plus cx3. What about x3? x3 is equal to bx2. This is our b, which is the transmittance. Substitute x2 in the equation of x3. So we've got x3 is equal to b, or x2 is equal to this. So we have substituted, and this is the same as we have expanded, and this is the same as x3. We're going to make x3 the subject of the formula, or we are going to arrange like terms together, x3 and x3. So this x3 minus bx3 is equal to this a bx1, and if we factor out x3, we are going to remain with 1 minus bc in brackets. This is equal to a bx1. So we are now going to find the ratio of output to input. So this is ab divided 1 minus bc. Hence we have got this expression there. And please take note that we have now separated the two. A, this our a, is used to multiply b over 1 minus bc. Please take note, this has all come from this equation with respect to x2 and equation with respect to x3. Please take note that on x2 we've got input and output. A representation of linear systems by signal flow graph, we've got this linear systems. X1 is equals to this, X2 is equals to this, and we have represented them by this signal flow graphs. As you can see, this is our U1, which is this our U1, and this is our X2, this is our X1. So we can say X1, want to make equations in terms of X1. X1 is equals to B1 U1, B1 U1 plus A11X1, A11X1. Then we've got also this incoming, which is equals to A12X1. So you take note of all incoming nodes. So 1, 2, 3, 1, 2, 3. Let's go to X2. This is our X2. We'll take also note of our incoming nodes. We've got A21X1, A21X1, then we've got this of loop, A22X2, then we've got B2U2. So this is how you represent linear systems by signal flow graphs. So given an equation like this, you must be able to represent it using signal flow graph. So we are saying the first equation, which is this equation, indicates that this X1 is equal to the sum of three signals. This signal, and this signal, because they are inflowing. And this represents X1. And our second equation indicates that this X2 is at the center, is a sum of this signal as well as this signal. We take note of incoming nodes. And we say this variable is represented by all outgoing nodes. So you ignore this because it is equal to the sum of all the incoming nodes, or all the nodes exactly. So it is the sum of X121, B2U2, and A22X2 as shown. How to change a block diagram to a signal flow graph? We've got this block diagram. It has got an input, a transfer function, which is also referred to as gain, and in SFG terms, it is referred to as transmittant. And this is the output response. In this case, it is Y of S. Please take note. So we want to represent this using the signal flow graph. We know that this represents the transmittance. So we've got one branch, so this is our branch between RS and YS, and our transfer function or gain becomes the transmittance as shown. In the second block diagram, we now have got a feedback loop, and this is what we call the error signal. Guys, you must be conversant with this now. So we've got how many nodes there? Please take note that the summing point is represented by a node. Then we've got the input node as well as the output node. Even in B, we've got the input node and the output node. And please take note that this is our feedback path, and it is represented by a negative transmittance. Please take note. So we are saying the overall gain from the input and output may obtain directly from the SFG by inspection, or we are going to use Mason's gain formula. Or it can also be done by a reduction of the graph to a simpler form. So please take note of the literature. The negative sign of the feedback path in C is included with a transmittance of H. We've looked, please take note that this is the transfer function. And from a transfer function, you can derive the block diagram. Please take note, this is our reference input, our output response, and our transfer function. And if we convert this to a signal flow graph, this is our input, our output, and this gain, this transfer function becomes our transmittance in this case. And we've got two parallel blocks connected in parallel, and this is, please take note that it is positive feedback because of the plus. So how do you represent this? We are going to change this to transmittance. Please take note that the two branches are parallel as shown, with each having its own transmittance as shown. How many nodes? We have got this node, the input, the output. Those are the two nodes that we've got. Please take note that this is the transfer function. We know this equation, and we know this is negative feedback because of the plus sign there, and this represents that it is negative feedback, and we want to represent this using the signal flow graph. We've got how many nodes? We've got the input and the output. The input node, then we've got this summing point. It is also represented by a node, and please take note this point is just the same as this point. What have we done? We have added this branch with a transmittance of 1. We have also added this branch with a transmittance of 1, so that we can have this input as well as this output. Please take note that the feedback path is represented by negative transfer function or negative transmittance, in this case negative HS. This is our gain, which is this gain. Please take note. The properties of signal flow graphs SFG. And what are we saying? We are saying they are used to represent linear systems. We saw when we represented linear equations using these SFGs. And we also know that the arrow indicates signal flow, and we know what a node is. It represents a variable or a signal. It can be an input signal, it can be an input node, an output node, etc. There is transmission of the value of a variable on each node, which leaves it. This we saw. Then a node adds the signals of all incoming branches and transmits the sum to all outgoing branches. I think you can deduce this when we represented the incoming branches for x1 and x2 as we were given in equations. And we are saying the algebraic sum of all signals entering a node gives the value of a variable at that node. We did that for x1 and x2. And we are saying since different system equations can be written, therefore signal flow graph of a system is not unique. The other property, using Maxwell's gain formula, the overall gain of a signal flow graph can be determined. After this, we'll be going straight into Maxwell's gain formula, which is used to find the overall transfer function of an SFG. Then a signal flow graph can represent a block diagram. Yes, we've just seen that, but the reverse is not true. Please take note. You can represent a block diagram using signal flow graph. Then the other property, a branch indicates functional dependence of one signal on the other. We saw that when we are linking two nodes, one signal will be depending on the other. Then the signal travels along the branch in the marked direction, and we know that it is multiplied by the transmitted or the gain of that particular branch. If you are not appreciating these properties, you can go back to the rules that we discussed. Then we also defined a mixed node, and we said it can be treated as an incoming and outgoing signals. There is a repetition there. A mixed node can be treated, let me wrap something, by adding an outgoing branch of unit transmittance. Then we are saying the gain on any path is equal to the product of all gains on that particular path. We saw this. Then the value of the variable represented by a node is transmitted on all nodes leaving that node. Guys, take note of these properties. They will help you to find the overall gain or the overall transfer function of a given signal flow graph. More on the properties of SFG, we are saying the overall gain or the overall transfer function of the SFG can be determined using Maxwell's gain formula. This is another property of a signal flow graph. Then a signal flow graph can represent a block diagram, but the reverse is not true. Please take note, we are going to derive an SFG from a block diagram. A branch indicates functional dependence of one signal on the other, we saw this, and we saw that x2 is equal to ax1. That's functional dependence. The signal travels along the branch in the marked direction, and it is multiplied by the gain of the transmittance of the branch. x1 is equals to x2 is equals to ax1. Then a mixed node can be treated as an incoming and outgoing signals by adding an outgoing branch of unity transmittance or of 1. Then the gain of any path is equal to this we saw and we derived. The gain of any path is equal to the products of all gains on that path. In other words, we would have reduced that SFG to just 2 nodes and 1 branch. Then last but not least, the value of the variable represented by a node is transmitted on all outgoing branches. Procedure when drawing signal flow graph, and we are saying replace all summing point by a node. Please take note that this is going to be represented by a node. Replace all takeoff points also by a node. Then replace all blocks by branches. And we are saying if the branch connecting a summing point and a takeoff point, like in this case a summing point and a takeoff point, then the summing point and takeoff point can be combined into one node as shown. There's a unit gain of 1. Hence we only have a single node to represent this and this. Hence this expression, the summing point and takeoff point represented by a single node. More on procedure, if there are more takeoff points from the same point, like in this case, more takeoff points, 1, 2, 3, but all are coming from the same signal, which is at this point, then all takeoff points can be combined and represented by a single node as shown. Hence, we are having H2 coming from the same point and H3 coming from the same point. So we are saying takeoff point is being replaced by a node. Then also more on procedure, if the link connecting two summing points, this is the link connecting this summing point to this summing point is 1, then the two summing points can be combined and replaced by a single node. Please don't note that this is the node representing the two summing points, and we still have our this a unit gain of positive 1, a gain of G1, and transfer function, which you could also refer to as a gain of H1. We are simply emphasizing the representation of two summing points connected by one link by just one node. We now want to go deeper or straight into Mason gain formula, and we are saying this is used to find the overall transfer function of a signal flow graph or to reduce signal flow graphs. And we are saying SFG can be reduced by using rules of SFG as we have seen, but we know that this is time consuming, and we are saying it is easier to use Mason's gain formula to reduce. We are saying Mason's gain formula developed, S.J.Mason developed a simple procedure for determining the transfer function of the system represented as a signal flow graph, and this procedure was named after him, Mason's gain formula, and it is useful in finding the transfer function of a system. In other words, you may encounter a question that asks you to find the transfer function for the ratio of CS to RS of a given signal flow graph, and you are requested to use Mason's gain formula. So guys, make sure you are able to do that. So follow very closely as we discuss Mason's gain formula. Mason's gain formula is a convenient and easy way of finding the relation between input and output system of outputs between input and output variables of a system. The only challenge with it is that it involves a number of steps in the block reduction method, and this is a time-consuming procedure. Take note that after implementing a rule, you must produce a diagram. So we are saying this is time consuming, but it is worth it. Disadvantage is that transfer functions are obtained directly without manipulation of the graph. Let us see. Mason's gain formula, and it is used to find the overall transfer function C of S divided by R of S, and it is given by 1 divided by determinant summation of from the first forward path gain to the last forward path gain multiplied by pk determinant subscript k, where k is the total number of forward path. So it's from the first forward path to the last forward path. And what do we represent by pk? This is the gain of the kth path, the kth forward path, you will see. So as I said in one of the slides, you must be able to identify forward path. If you cannot identify forward paths, then you cannot be able to use Maxwell's gain formula. Then this delta is equal to the determinant of the graph. Please take note of how you find the delta or the determinant of the graph. Rather, 1 minus sum of all individual loop gains, including self loops. You also add sum of all gain products of all possible combinations of 2 non-touching loops. You go to 3 non-touching loops, etc., etc. Then this represents the value of the determinant after eliminating all loop gains and associated paths that touch our forward path. So what am I saying? Must be able to identify forward paths, must be able to identify loop gains. You also must be able to identify touching and non-touching loop. You also must be able to identify loops that touch the forward paths. It's now question after question until we finish. So pay attention of how you approach each question. We are saying, find the transfer function of the system shown below using Maxwell's gain formula. And this is our signal flow graph. And the first step is identify the number of forward paths and their gains. So we've got, this is very easy. We've got how many forward paths? We've got 2. Please, you ignore this. This is not a forward path. This is a feedback path. So we've got this path by G3, and you've got this path where you go straight up to C of S from R of S. So we are saying there are 2 forward paths and their gains are. This is 1 times G1 times G2 times G4 then times 1. We are done. This 1 and 1 give us 1. So we can leave them. G1, G2 and G4. Then gain of the second path. Gain of the second path. This is our second path. This is according to me. You can say this is your forward path and this is your second path. It doesn't change anything. This is 1 times G1 times G3 times G4 and times 1. You are done. So that K in Maxwell's gain formula, which is this K, which is also from 1 up to K according to the summation sign, is in this case it is equal to 2. After identifying forward paths and their gains, we are proceeding to find the individual loops and also their gains. Guys, what you call L1, L2, L3, we don't care. As long as you are identifying each loop, that's fine. So we are saying, I have called the first loop L1. L stands for the loop, and this is my first loop. From this node and back to this node. So we are going this way. So we call this a loop. So it is G1, G2 and minus H2. Let's go to the second loop. According to me, this is my second loop from this point via G4 minus H1 and back to this point. So it is a loop. So this is equal to minus G4 H1. My third loop is from, let me see, this is from this point. And let us proceed. This is 1 times G1 times G2 times G4 times minus 1 in this case. We are now going back to where we came from. So this is my third loop. So when simplified, it is simply going to be this. And my fourth loop, even if you are not able to identify, just follow me. It's it's plus G1. After G1, we are going via this route to G3, G4, then we are coming back from where we came from. So there are 4 individual loops and these are their gains. If you cannot find the gains, then guys, you will lose a lot of marks, because Maxwell's gain formula has got a lot of respect in examinations and it has got a lot of marks. So guys, this is our second step. We are proceeding to the third step. Third step, we are now finding the non-touching loops and their gains. So we call this find combination of non-touching loops. Right, I'll flip and go back to our signal flow graph. And this is our signal flow graph. We've got, right, loops are non-touching if they've got no node in common. So in this case, we've got this loop and this loop. They have no node in common. So we say they are non-touching. So the combination of 2 non-touching loops, L1 and L2, this is the gain of loop 1, this is the gain of loop 2, and this is our overall gain. and we are saying there is no other combination of two or more non-touching loops. So for our step 4, we are now going to find the determinant of the graph. And how do you find the determinant of graph? We are going to take cognizance of all our gains that we found. So we are going to say 1 minus sum of individual loop gains plus sum of gains of non-touching loops minus the sum of products of all combinations of 3 non-touching loops or more. So according to us, we've got determinant is equals to L1, L2, L3, L4. These are the gains of the loops plus the combination of non-touching loops. We don't have the sum of products of 4 combinations of 3 non-touching loops. We don't have higher order non-touching loops, so we are going to end there. If we simplify there, our determinant is going to be this. So this determinant is this determinant. We are not yet done. The 4th step, we are now going to find the value of this function, the determinant subscript k. And how do you find it? We eliminate all loop gains and associated products which touch the kth forward path. This is after identifying the number of forward paths we might behave 2, 3, 4, etc. So all loop gains and associated products which touch any path must be eliminated. And please take note that it's 1 minus. So what do? We are saying from the SFG, all the loops touch the forward paths. So under such case, if we eliminate, it means that the determinant of 1 is equal to the determinant of 2, because we have got 2 forward paths, and this is going to be 1. Why? Because we've eliminated the gains of loop gains of non-touching of 4 associated products which are touching all forward paths. So we are now going to Mason's gain formula. And since we know that our k is equals to 2, so this is summation from k is equals to 1 to k is equals to 2 from the first forward path to the second forward path. And we are going to multiply this by the gain of the kth path multiplied by this value there. And we have got 2 forward paths, P1 multiplied by the determinant of the first path multiplied by the gain of the first path, the determinant of the second path, or this is divided by the determinant. So we are going to put the values. This value, please take note, it is equals to 1. It does not necessarily mean that this value of is always equal to 1. No. So this also value is equal to 1. And we've just found this is equal to this. So this is your answer. The overall transfer function using Mason's gain formula is equal to this. In other words, we have reduced the signal flow graph. We have got this input, and this is our gain. We simply have got one node with this gain or with this transmittance. Another question. We've got a signal flow graph, and the question says find the transfer function of the system, which is this system using Mason's gain formula. The first step, the forward paths of the given signal flow graphs are shown. This is the first forward path, simply goes straight, and please take note that we've included dummy loads there, but we don't care. Then the other forward path is from there to there to there, and this is our forward path. You are done. You get marks for these guys, even if you eventually fail to find the overall transfer function. You get marks for this. So make sure you label each step. You also get marks for calculate the loop gains. And in other words, our step 2, we've got this is a loop, this is a loop, and those are the only loops that we have. So our first loop is G1, G2 times minus H1. Then our second loop, G2, G3 times minus H2. We are done. We found the gain of the individual loops. Then do we have non-touching loops? No. This loop is common to this loop. This loop is common to this loop. So we don't have non-touching loops. You get marks for this statement. Take note, you get marks for this statement. Then we are now going to find the determinant. So this is equal to 0. So it's 1 minus the gain of the loops, So this is going to give us 1 plus this, and we are now going to our step 5. We are saying loop 1 and loop 2 touch the first forward path, so it means that this is equal to 1. Then for our second forward path, we are saying loop 1 and 2 touch, therefore its determinant is equal to 1. Let us go and finalize. Right, this is our final step, and this is our Mason's gain formula. Gain of the first part, which is this multiplied by 1, plus the gain of the second part, which is this multiplied by 1, or divided by the determinant of the signal flow graph. So this is the solution. Another question, find the transfer function of the system with this SFG. Please take note of our feedback path transmittance. Minus H4, minus H3, minus H2, and minus H1. This was wrong it had no negative sign in the initial PDF lecture notes that I gave you, so I will have to resend them, but don't worry. So we will start by finding the forward paths, and this first from RS to CS, this is our first forward path. This is not a problem. G1, G2, G3, and G4. This 1 and 1 that do not change anything. It will mean a 1. So this is our first forward path. This is our second forward path, and it is now going via G5, via this path. This transmittance, this branch. So it's 1 times G1 times G3 times G4 times 1. It's simply G1, G5, and G4 in that order. And now identifying the loops. You get marks from identifying the loops. Even if you fail to calculate, or true has to calculate their gains. So this is my first loop, which is equal to this loop. So what is its gain? It's minus G1 H1. This is my second loop, which is equal to this, and what is its gain? G1 minus G1 G2 minus H2. This is my third loop, which is equal to G2 G3. This is my third loop, G2 G3 and minus H3 gives you this gain. This is my fourth loop, minus G4 H4, and this is my fifth loop. This G5 minus H3. Please take note, guys. And if you are learning something, guys, don't be afraid to hit the subscribe button. It is you guys who make Telecom Academy great. Now going to identify non-touching loops, because this must be subtracted for us to. So it is an important parameter. So the loops that are not touching are 1 and 4 and 2 and 4, and we are going to multiply their gains. So this is going to be the gain of loop 1 and 4 and the gain of loop 2 and 4. Please take note. So we are now going to this was step 3, we are now going to step 4. There are no higher order loop whereby we've got 3, 4, 5. We are now adding 8. These two non-touching loops. So what is our determinant? It's 1 minus the gain of the loops minus the gain of non-touching loops. And if you simplify, you are going to get this. Then we are now going to make use of Mason's gain formula. This plus this. But please take note that all our loops are touch the forward path. So this is equal to 1, and this is equal to 1. If we eliminate them, so eventually this is our transfer function of this signal flow graph. Guys, this is for you, and you've got A and B. Find the transfer function using Mason's gain formula of the systems below. If you do this and you check with me, you can just send me a screenshot of your solution on my WhatsApp number, and I will give you a feedback. Ignore this to your own peril. We have covered block diagram, and we've just covered signal flow graph. So compare the two and see if it makes sense.